Our universe hides its greatest secrets behind veils of cosmic dust. The Spitzer Space Telescope was our infrared key to unlocking them, revealing a hidden cosmos of star birth and alien worlds. By the end of this journey, you will understand how this one telescope rewrote our cosmic story and set the stage for technologies that will shape our future. We will uncover how it peered into stellar nurseries no other telescope could see, and what its discovery of 7 Earth-sized planets means for our search for life. What does a hidden universe reveal about our own place within it? Human eyes are incredible, but they are tuned to see only a narrow band of reality. We call this visible light, and it is merely one sliver of a vast cosmic rainbow. The universe is constantly broadcasting across this entire spectrum, from high-energy gamma rays to long, lazy radio waves. For centuries, we were deaf to most of this symphony, staring up at the stars and seeing only what our biology allowed. The iconic Hubble Space Telescope, for all its power, primarily observes this same familiar realm of visible and ultraviolet light. It gives us breathtaking portraits of galaxies, but it cannot see through the thick, dark clouds of cosmic dust that fill space. These dust clouds are not like earthly dirt. They are vast, cold nurseries light years across where new stars and planets are actively forming. To Hubble's eye and to ours, these regions appear as impenetrable black voids, empty and silent. But that silence is an illusion. The secret lies in the nature of light itself. Visible light waves are relatively short and are easily scattered or absorbed by these dust grains, like a car's headlights being swallowed by a dense fog. Infrared light, however, has longer wavelengths. These waves can slip right between the dust particles, largely unaffected. The heat and glow from the stellar embryos hidden deep within these clouds is emitted not as visible light but as infrared radiation. So, to witness the birth of a star, we could not rely on the eyes we were born with. We needed a new kind of vision. We needed an infrared eye that could cut through the cosmic fog and see the warm glow of creation itself. This was the fundamental cosmic need that the Spitzer Space Telescope was born to fulfill. It was our window into the universe's most secretive and sacred places. Such a powerful vision could not be built in a day. The story of the Spitzer Telescope, known for decades by its working name, the Space Infrared Telescope Facility, is a testament to human persistence. Its journey from a bold idea on a chalkboard to a working observatory in the dark of space took nearly half a century. The initial concept was proposed in the 1970s, a time of great ambition for astronomy. Scientists dreamed of a large, powerful infrared telescope that could orbit far above Earth's obscuring atmosphere. But the technology to build such a machine and the money to pay for it simply did not exist yet. The project was perpetually stuck in the planning stages, a dream deferred by technical limitations and the harsh reality of budget cycles. For years, it survived only as a set of blueprints, constantly being redesigned to be more capable, yet cheaper and smaller. It faced cancellation multiple times, a ghost of a mission that refused to die. The teams behind it had to make painful compromises, scaling down their grand visions into something that could actually be built and launched. The final design was a masterpiece of engineering creativity. Instead of circling the Earth, where our planet's own heat would blind its sensitive infrared eyes, Spitzer would be sent into a revolutionary new type of orbit. It would trail behind Earth in its journey around the Sun, slowly drifting farther away over the years. This Earth-trailing orbit placed it in the profound cold of deep space, a perfect environment for an infrared telescope to do its work. The struggle to get Spitzer off the ground defined its very identity. Every component, from its unique orbit to its sun shield, was a direct answer to a challenge that had threatened to kill the project for 40 years. This was not a machine that appeared overnight. It was forged in the fires of perseverance, a monument to the scientists and engineers who never gave up on the dream of seeing the hidden universe. To see the faint warmth of cosmic creation, Spitzer itself had to become profoundly cold. Its entire mission depended on achieving a state of near-absolute stillness, a technological deep freeze unlike anything attempted before. The heart of the telescope was a tank of liquid helium, a supercoolant that chilled its three primary instruments to a staggering -267 degrees Celsius. That is just a few degrees above the theoretical point of absolute zero, the temperature where all atomic motion ceases. This was not a luxury, it was an absolute necessity. Spitzer was designed to detect the faintest whispers of infrared heat from across the galaxy. If its own components were warm, even at room temperature, they would glow brightly in the infrared spectrum. This self-generated heat would completely drown out the faint signals from distant nebulae and forming planets, like trying to hear a pin drop in a roaring thunderstorm. The cryogenic system was a masterpiece of insulation, a thermos bottle on a cosmic scale, designed to keep this precious cold locked in for as long as possible. But cold was only half the battle. Spitzer also had to hide from the sun. The telescope was equipped with a massive, innovative sun shield, always pointing away from our star. This shield acted like a parasol, casting the observatory's delicate instruments into a permanent, deep shadow. While one side of the spacecraft baked in direct sunlight, the other side, where the telescope peered into the void, remained in the frigid darkness of space. This clever design, combining a cryogenic heart with a solar umbrella, created the stable, ultra-cold environment Spitzer needed to open its infrared eyes. It was a delicate ballet of extreme temperatures, a dance between shadow and cold that allowed humanity to finally perceive the hidden warmth of the universe. Spitzer was never meant to work alone. It was the final piece of a grand astronomical strategy, the last of 4 siblings sent to see the universe in lights no human eye could perceive. NASA called this family the Great Observatories, and together they formed a complete sensory suite for the cosmos. Each one was a specialist tuned to a different part of the electromagnetic spectrum. The Hubble Space Telescope was the master of visible and ultraviolet light, giving us those iconic, crystal-clear portraits of galaxies and nebulae. But as we learned, Hubble sees the universe as we do, and it is blind to the dust-shrouded theaters of star birth. Then there was the Compton Gamma Ray Observatory, a powerhouse designed to capture the most violent and explosive events in the universe, the death cries of massive stars and the collisions of neutron stars, all broadcast in the highest energy gamma rays. Its sibling, the Chandra X-ray Observatory, peered into the searingly hot realms, mapping the remnants of supernova explosions and the intense gravity wells around black holes, where matter is heated to millions of degrees and glows in X-rays. And then, completing the set, was Spitzer, the quiet specialist in the cool and the hidden. Its infrared vision was the perfect counterpoint to its brothers and sisters. Where Hubble saw a dark void, Spitzer saw a glowing stellar nursery. Where Chandra saw the superheated aftermath of a star's death, Spitzer could often see the cold, raw materials that would one day form new stars. They were not competitors, they were collaborators. A single cosmic event like a galaxy collision would be observed by all 4. Hubble would map the graceful swirls of existing stars. Chandra would pinpoint the raging infernos of new black holes. Compton might detect a burst of gamma rays from the chaos, and Spitzer would reveal the hidden shockwaves of dust and gas, the invisible fuel for the next generation of stars being born from the wreckage. This multi-wavelength vision allowed us to see the universe not as a collection of separate snapshots, but as a single, dynamic, and interconnected system. Spitzer's unique ability to sense the cold and the old gave the family's portrait of the cosmos its depth and warmth, revealing the hidden foundations upon which everything else is built. That long-awaited launch finally came on August 25, 2003. A Delta II rocket lifted off from Cape Canaveral, carrying the hopes of decades into a clear blue sky. For the scientists and engineers who had dedicated their careers to this moment, it was a culmination of a lifetime's work. The spacecraft, now officially named the Spitzer Space Telescope in honor of the visionary astrophysicist Lyman Spitzer Jr., who first championed the idea of space observatories, was on its way. The first critical days in space were a tense ballet of careful commands. The sun's shield had to deploy perfectly, orienting the telescope into its permanent shadow. The lid covering the telescope's mirror had to be jettisoned, opening its eye to the cosmos for the very first time, and then the moment of truth arrived. The first data began to trickle back to Earth. The team held its breath, waiting to see if this complex machine, forged from compromise and perseverance, would actually work. The answer came not in a stream of numbers, but in a picture. Spitzer turned its infrared gaze toward a seemingly dark cloud of dust, a region that optical telescopes like Hubble saw as little more than a blank spot in the sky. The image that came back was not dark at all. It was a spectacular, swirling tapestry of light, a glowing crimson nursery teeming with embryonic stars and the swirling disks of dust that would one day become planetary systems. This was not just a successful test, it was a revelation. The telescope was not merely functioning. It was performing so far beyond its design specifications that it was instantly clear a new era of astronomy had begun. Spitzer's flawless vision confirmed that the universe was not the quiet, static place it sometimes appeared. It was a vibrant, dynamic, and hidden landscape, now suddenly and brilliantly illuminated. With its eye now open to the universe's hidden light, Spitzer immediately began to transform our cosmic cartography. Its greatest power was its ability to see through the walls of stellar nurseries, places like the magnificent Orion Nebula. To every other telescope, these were beautiful but opaque clouds, their deepest secrets locked away behind veils of dust. Spitzer's infrared vision acted like a pair of cosmic X-ray glasses, letting it peer directly into the heart of these nebulae. What it found there was a chaotic and vibrant construction site on an unimaginable scale. It saw protostars which are not yet true stars but dense, collapsing knots of gas and dust, glowing with the heat of their own gravitational birth pangs. These are stellar infants, still swaddled in their thick, dusty blankets, and completely invisible to telescopes that rely on visible light. Spitzer did not just see these infant suns as points of light. It saw the structures around them, the swirling, flattened disks of material left over from the star's formation. These are protoplanetary disks, the raw stuff of future solar systems. Within that swirling chaos of rock and ice, the first planets were beginning to clump together, their orbits clearing paths in the cosmic dust. For the first time, we were not just theorizing about how planets form. We were watching it happen in real time across hundreds of examples. Spitzer revealed that star birth is not a gentle process, but a violent and messy one, where powerful jets of material scream out from the infant star's poles, carving vast cavities in the surrounding cloud. The telescope showed us that our own solar system likely began in a similar frenzy of creation, within a nebula not so different from Orion. It connected our local cosmic neighborhood to a universal process, a continuous cycle of birth happening all across the galaxy, hidden in plain sight until Spitzer turned its infrared gaze upon it. The iconic Pleiades cluster has captivated humanity for millennia, a tiny shimmering dipper of stars we thought we knew. But Spitzer's infrared vision peeled back that familiar glitter to reveal a hidden architecture. It saw not just the brilliant, hot stars, but the faint, warm glow of dust surrounding them. This was not a uniform cloud. Spitzer mapped vast, intricate webs of cosmic debris, delicate filaments and ripples stretching far beyond the visible stars. These intricate structures told a dynamic story. The dust is not simply left over from the cluster's birth. It is being pushed and sculpted by the stars themselves. The intense radiation and powerful stellar winds from the young, energetic Pleiades sisters are actively blowing the dust away, carving immense cavities and shaping the filaments we see. This revealed a crucial clock for the cluster's future. By measuring the amount and distribution of this dust, astronomers could estimate how much raw material remains. They realized the Pleiades is in the process of dispersing its own nursery. The very stars that give it light are simultaneously destroying the dusty cradle that formed them. This delicate interplay between creation and dissolution gave us a profound new understanding. Star clusters are not permanent fixtures in the sky. They have a life cycle, a youth defined by dusty shrouds, and a maturity where they blow those shrouds away. Spitzer showed us the Pleiades at a pivotal moment in its life, actively cleaning its house and destined to eventually drift apart. The telescope transformed this beautiful sight from a static picture into a snapshot of an ongoing cosmic story, a fleeting chapter in the life of a star cluster. Our own galaxy, the Milky Way, has always presented a profound puzzle. From our position within its disk, the central plane of the galaxy appears as a hazy, luminous band arching across the night sky. But peer closer with an optical telescope, and that majestic river of light dissolves into a murky fog, its core details lost to the very dust that fills the space between the stars. We were like mapmakers stranded in a dense forest, unable to see the shape of the woods for the trees. Spitzer set out to change that with one of its most ambitious projects, the Galactic Legacy Infrared Mid-Plane Survey Extraordinaire, known simply as the Glimpse Survey. This was not a brief observation but a monumental, multi-year cartographic mission. Spitzer slowly and methodically scanned the entire disk of our galaxy, stitching together over 400,000 individual images into a single, seamless, high-resolution infrared map. It was as if we had been given a pair of goggles that could see through the smog, revealing the true metropolis of stars beneath. The sheer scale of the data was staggering. The Glimpse survey catalogued over 100 million individual stars, most of them previously hidden from our view. It revealed vast, bubbling bubbles of gas blown by the winds of massive stars, intricate networks of dark filaments, and the glowing clouds of complex carbon molecules that are the building blocks of life. For the first time, we could trace the grand spiral arms of our galaxy, not just by the brilliant, hot stars that outline them, but by the warm glow of the countless smaller, cooler stars that form their backbone. This new map showed our galaxy not as a static picture, but as a dynamic ecosystem, a living entity where structure emerges from chaos. It was a census of our cosmic neighborhood on an unimaginable scale, a foundational dataset that will guide astronomers for generations to come. What other secrets long hidden in the dust might this new map of our home galaxy still be concealing? Spitzer's detailed map of the Milky Way gave us an unprecedented view of our home, but it came with a fundamental limitation. We are trapped inside the very structure we are trying to understand, making it impossible to see the galaxy's true shape and architecture from within. To truly comprehend the grand design of a spiral galaxy like our own, we needed to step outside and look at a neighbor. The telescope's gaze therefore turned to the Andromeda Galaxy, a swirling island of 1 trillion stars lying 2.5 million light-years away. This was the perfect cosmic laboratory, a spiral galaxy similar to our own, but one we could observe from the outside in its entirety. With its infrared eyes, Spitzer did not just take a pretty picture of Andromeda. It conducted a meticulous stellar census, piercing through the galaxy's obscuring dust lanes to take an inventory of its stars and the raw materials between them. The resulting mosaic was a masterpiece of cosmic cartography, containing a staggering 1 billion individual pixels, each one telling a part of the story. Spitzer's vision revealed the cold, old stars that form the galaxy's backbone, stars that are often hidden in visible light images dominated by the hot, blue, and short-lived giants. It meticulously charted the complex structure of Andromeda's spiral arms, not just by the brilliant young stars, but by the warm dust that traced their contours like luminous cobwebs. This dust is not mere decoration. It is the frozen reservoir for future generations of stars and planets. By measuring its amount and distribution with such precision, Spitzer gave us a template, a universal blueprint for how a typical spiral galaxy organizes its material. The telescope showed us that Andromeda is not just a distant smudge of light. It is a dynamic, structured, and complete stellar ecosystem, a mirror held up to our own Milky Way. In studying its intricate details, we were, for the first time, learning the full story of our own galactic home by reading its reflection in the cosmic pond. Deep within the cosmic nurseries Spitzer unveiled, not every story ends in starlight. Some celestial objects are born into a permanent twilight, too massive to be called planets yet lacking the gravitational might to truly ignite. These are brown dwarfs, the failed stars of the cosmos, and Spitzer became a master hunter of these elusive shadows. A brown dwarf forms like a star from a collapsing cloud of gas and dust, but it never reaches the critical mass needed to sustain the nuclear fusion that powers a sun. It is a cosmic ember glowing faintly with only the residual heat of its violent birth. To our eyes and to most telescopes, these objects are nearly invisible, emitting almost no visible light. Their story is told entirely in the infrared as a soft, warm glow against the cold backdrop of space. Spitzer's sensitive infrared detectors were perfectly tuned to pick up this faint signature. The telescope scanned star-forming regions and isolated patches of sky, identifying countless points of infrared light that optical surveys had missed. By carefully analyzing the color and intensity of this infrared glow, astronomers could distinguish a cold, distant brown dwarf from a hot, distant star or a nearby planet. Each discovery was like finding a ghost, a massive object that had been hiding in plain sight, rewriting the census of our solar neighborhood. Why does the existence of these failed stars matter so profoundly? They represent a crucial missing link in our understanding of star formation. They are the natural boundary between the realm of planets and the realm of stars. By counting them and studying their properties, Spitzer helped astronomers answer a fundamental question: how small can a star actually be? The population of brown dwarfs reveals the lower limit for stellar success, showing us where the physics of star formation gives way to the physics of planet formation. They are the cosmic also-rans, the objects that almost made it, and their very presence helps us understand why some collapsing clouds become brilliant suns while others fade into a dark and warm obscurity. What other faint signatures, lost between the categories we understand, might still be waiting for the right kind of vision to be seen? Spitzer's hunt for failed stars was just the beginning of its detective work. This same sensitivity to faint, warm objects positioned it for one of the most unexpected revolutions in modern astronomy: the study of planets orbiting other stars. Initially, no one had designed Spitzer to be an exoplanet hunter. Its mission was to observe the cold and the distant, not to track the subtle dance of alien worlds. Yet its unparalleled stability and its infrared vision made it the perfect instrument for a new kind of investigation. The primary method involves watching for a transit, the tiny, periodic dimming of a star's light as an orbiting planet crosses directly in front of it. For most telescopes, detecting this dip is challenging enough, but Spitzer could go much further. When the planet passes behind its star, vanishing from view, the telescope measures the infinitesimal drop in the total infrared light from the system. This decrease is the direct heat signature of the planet itself. Think of it as listening for the quiet hum of a single refrigerator in a power plant. By comparing the light when the planet is visible to when it is hidden, astronomers could subtract the star's overwhelming glare and isolate the faint infrared glow of the planet alone. This simple yet profound act of subtraction allowed Spitzer to become the first telescope ever to directly measure the temperature of a world outside our solar system. It revealed scorching gas giants orbiting blisteringly close to their stars, with dayside temperatures hot enough to melt iron. but it also found more temperate worlds, suggesting a far greater diversity of planetary environments than we had ever dreamed. The telescope's infrared eyes could even analyze the atmospheric composition of these distant orbs. As the planet transits its star, a sliver of the star's light filters through the planet's atmosphere. Different molecules in that alien air absorb specific wavelengths of infrared light. By carefully dissecting this filtered starlight, Spitzer could identify the chemical fingerprints of water vapor, methane, and even silicate clouds in the skies of these hot Jupiters. It was as if the telescope could taste the air on a world light years away. How could a telescope built to see stellar nurseries become our most capable instrument for sniffing the atmospheres of alien worlds? It was a beautiful accident of design, a testament to the versatility of a machine that saw the universe in the warmth of hidden things. Spitzer's unique talent for sensing distant warmth reached its pinnacle in a quiet, unassuming star system known as TRAPPIST-1. This ultra-cool dwarf star, smaller and redder than our Sun, seemed an unlikely setting for a cosmic breakthrough. Yet it was here, 40 light-years away, that Spitzer unveiled its most stunning discovery. Not just one, but 7 rocky planets, all nearly the size of Earth. The telescope's role was absolutely critical. Unlike larger, hotter stars, TRAPPIST-1 is so faint and cool that its planets orbit incredibly close, completing their years in just a handful of Earth days. This fast orbital dance meant that to confirm the planets, astronomers needed to watch for repeated, rhythmic dips in the star's light as the planets transited again and again. Spitzer was the only observatory with the patience, the stability, and the sensitive infrared vision to observe this complex celestial clockwork for weeks on end without interruption. It monitored the star for over 500 continuous hours, capturing the faint, repeating shadows of all 7 worlds with flawless precision. This was not a single snapshot, but a long, unblinking stare that revealed an entire solar system in miniature. But Spitzer did more than just count the planets. By measuring the exact depth and timing of each transit with incredible accuracy, it provided the data to weigh these worlds. Astronomers could calculate their densities, confirming they were not gaseous giants but solid, rocky bodies like Mars, Venus, or Earth. The telescope's data even hinted at their compositions, suggesting some could hold vast amounts of water. 3 of these 7 siblings orbit within the star's habitable zone, that temperate band where temperatures could allow liquid water to pool on the surface. Spitzer's prolonged gaze transformed TRAPPIST-1 from a single star into a full-fledged planetary system, a place that represents our best chance yet of finding an environment similar to our own. It gave us a tangible target, a nearby laboratory for the next generation of telescopes to scour for signs of atmosphere and perhaps for the subtle fingerprints of life. What might we learn when we finally train our most powerful eyes on this family of Earths, a system whose very existence we owe to an infrared telescope's patient watch? Spitzer's ability to weigh rocky worlds was just one facet of its alien planet expertise. Its most revolutionary work lay in sniffing the very air of distant gas giants, a feat that seemed like science fiction at the time. The telescope became a master atmospheric detective for a class of planets known as hot Jupiters. These are colossal worlds, many times the mass of our own Jupiter, that orbit so close to their stars that their years last only a few Earth days. This proximity makes them infernos, but it also makes them perfect laboratories. When a hot Jupiter transits in front of its star, a tiny fraction of the star's light passes through the planet's outer atmosphere before continuing on to us. Spitzer's infrared eyes were uniquely equipped to analyze this filtered starlight. Different molecules in the planet's air absorb very specific colors or wavelengths of infrared light. Water vapor, for instance, soaks up certain bands while methane blocks others. By carefully splitting the star's faint infrared glow into a spectrum, a rainbow of heat, astronomers could look for the telltale dips and lines that betrayed the presence of these chemicals. It was akin to taking a distant, searingly hot world and holding a prism up to its shimmering outline, reading the chemical barcode imprinted on its light. Spitzer did not just detect these molecules in a handful of cases. It confirmed water vapor on multiple worlds, found the signatures of carbon dioxide and methane, and even mapped the temperature of these planets, revealing permanent daysides of molten rock and violent supersonic winds that redistributed the blistering heat. This was not merely observation, it was the birth of a new science, comparative exoplanetology. For the first time, we could move beyond simply finding new worlds and begin to compare the weather and chemistry of one alien atmosphere against another. Every analysis was a proof of concept, a demonstration that the atmospheres of worlds light years away were not beyond our reach. The techniques and data processing methods painstakingly developed for Spitzer's observations became the foundational playbook. They provided the essential training wheels for its colossal successor, the James Webb Space Telescope. When Webb today points its golden mirror at a distant, rocky world in a habitable zone searching for the subtle, combined fingerprints of oxygen, methane, and water that might hint at life, it is walking a path first cleared by Spitzer's pioneering infrared gaze. The hunt for biosignatures, the ultimate cosmic quest, owes its very methodology to the telescope that first taught us how to taste the air of another world. While Spitzer's gaze often stretched across light years to alien solar systems, it also delivered profound insights about our own cosmic neighborhood. This powerful telescope turned its infrared eye toward the comets and asteroids whizzing past Earth, transforming them from faint points of light into richly detailed worlds. A comet, for instance, is far more than an icy wanderer with a glowing tail. It is a frozen time capsule holding pristine material left over from the solar system's birth. When Spitzer observed comets like Tempel 1 and Hartley 2, it did not just take their picture. It analyzed the warm glow of the dust and gas in their comas, the bright clouds surrounding the nucleus. Every mineral and molecule in that ejected material has a unique infrared signature. Spitzer's spectrograph acted like a cosmic chemist, identifying the specific ingredients in that primordial soup. It found water ice, of course, but also a zoo of complex organic compounds, including carbon dioxide, methane, and even the building blocks of amino acids. This was a staggering revelation. The same raw materials that combined to form our planets, and perhaps even to seed life on Earth, were being delivered to our doorstep by these icy messengers from the outer solar system. Each comet became a piece of the puzzle, telling us what the recipe was for building our own world. How did the composition of a comet from the Kuiper belt differ from one from the distant Oort cloud? Spitzer's data helped us classify them, tracing their origins and understanding the different conditions in the early solar system that forged them. The telescope showed us that these spectacular visitors are not just celestial fireworks. They are the preserved leftovers from our own construction site, and their chemistry tells the story of our beginnings. This same analytical power was applied to the asteroids lurking in the belt between Mars and Jupiter. To an optical telescope, most asteroids are just faint, moving dots, but Spitzer could sense the heat radiating from their sun-baked surfaces. By comparing the infrared heat with the visible sunlight they reflected, astronomers could determine a crucial property, the asteroid's size. This sounds simple, but it is revolutionary. Before Spitzer, we could only guess at the size of most asteroids based on their brightness, a method full of uncertainty. A small, bright asteroid could look identical to a large, dark one. Spitzer cut through this ambiguity. Its infrared measurements gave us the true size, and when combined with the visible light data, it revealed the object's albedo, or how dark its surface is. This was like turning on the lights in a dark room. We discovered that the asteroid belt is filled with a stunning diversity of worlds. Some are as black as coal, ancient and pristine, while others are as bright as fresh asphalt, suggesting they have been recently shattered and broken apart, revealing brighter interiors. Spitzer went even further, identifying the mineral composition of asteroid surfaces. It found asteroids rich in olivine, a greenish mineral that forms deep inside planets, and others coated in complex organic molecules. These were not just random rocks, they were the shattered remains of failed planets, each type telling a different chapter of the solar system's violent early history. By cataloging their compositions and sizes, Spitzer helped us understand the architecture of our planetary system and the building blocks that never managed to coalesce into a larger world. Perhaps Spitzer's most immediate contribution to our future was its role in planetary defense. The threat of an asteroid impact is a real one, and the first step in assessing that risk is knowing what these objects are made of. A solid metallic asteroid would behave very differently upon atmospheric entry than a loose rubble pile. Spitzer's size and composition data for near-Earth asteroids provided critical intelligence. A small, dense asteroid could potentially cause significant damage, while a larger, porous one might break apart harmlessly in the atmosphere. By studying the orbits and physical properties of these potential hazards, Spitzer supplied the essential data needed to model impact scenarios and eventually to develop strategies to deflect a dangerous object. Its legacy in this field is one of quiet vigilance. The telescope showed us that understanding our solar system is not just an academic exercise. It is an act of stewardship for our planet, a way to read the history written in the rocks around us while also safeguarding the future. The same infrared vision that revealed the birth of stars in distant nebulae was also employed to protect the world beneath our feet, proving that exploring the cosmos and preserving our own home are two sides of the same coin. What other secrets, both of our past and our future, are still orbiting silently in the darkness, waiting for the right kind of light to reveal them? Spitzer's vision captured not only the gentle glow of creation, but also the violent, brilliant finales of massive stars. When a star many times larger than our Sun exhausts its nuclear fuel, its core collapses in a cataclysmic explosion known as a supernova. For a few brief weeks, this single star can outshine its entire galaxy. But what happens next is just as important as the blast itself. The star's outer layers are hurled into space at millions of miles per hour, creating an expanding fireball of incandescent debris. While visible light telescopes see a fading point of light, Spitzer's infrared eyes perceived the enduring echo of that violence. It studied the supernova remnants, the vast, expanding clouds of gas and dust left behind. These clouds are far more than cosmic gravestones. They are tremendous forges, and Spitzer became their chemist. Within the unimaginable heat and pressure of the explosion, atoms are fused together into new, heavier elements. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were forged in the heart of a long-dead star and then scattered across the galaxy by a supernova blast. Spitzer could identify the specific dust grains and molecules within these remnant clouds. It detected signatures of silicates, the stuff of sand and rock, and complex carbon compounds, the essential ingredients for life. The telescope revealed that these expanding shells are incredibly efficient dust factories, generating immense quantities of fresh raw material. This stardust, enriched with new elements, eventually mixes with the surrounding interstellar gas. Over millions of years, gravity pulls these enriched clouds together, and within them, a new generation of stars and planets begins to form. Our own solar system is built from the ashes of such an explosion. Every planet and every living thing on Earth is literally made of recycled stardust. Spitzer showed us that the spectacular death of one star is the necessary precondition for the birth of future worlds, linking the end of a stellar life to the beginning of our own. What other elemental secrets scattered by ancient blasts are still drifting between the stars, waiting to become part of something new? Spitzer's vision stretched even beyond the stellar life cycle, reaching across the vast emptiness to witness the universe's very first light. To see the most distant galaxies is to look back in time, their light traveling for billions of years before finally reaching us. Yet that ancient starlight faces a cosmic obstacle. The universe itself is expanding, stretching the fabric of space and shifting the light from these early galaxies out of the visible spectrum and into the infrared. This effect, called redshift, meant that Hubble, for all its power, could only see these infant island universes as faint, dark smudges. Their true story was locked in infrared wavelengths, and that is where Spitzer's unique sensitivity became indispensable. Working in tandem, Hubble would first identify these incredibly faint, redshifted blobs, and then Spitzer would point its infrared eye at them to measure their warmth and size. By combining Hubble's sharp vision with Spitzer's ability to see the heat of their stars, astronomers could perform a kind of cosmic census on the early universe. They discovered that some of these galaxies were forming stars at a ferocious rate, hundreds of times faster than our own Milky Way does today. They were cosmic firestorms, building their structures in a frantic rush during an era just a few 100 million years after the Big Bang. Spitzer revealed that these early galaxies were also surprisingly massive, packed with old, red stars that had already lived and died. This was a revelation. It meant that the first galaxies assembled themselves with breathtaking speed, maturing far earlier in cosmic history than anyone had predicted. The universe's childhood was not a slow, gradual awakening, but an explosive period of intense and rapid construction. How did such colossal structures form so quickly after the birth of everything? The data from Spitzer and Hubble suggested a universe that got to work immediately, forging the first cities of stars in the profound darkness of deep time. Every great mission must eventually face its limits. After 5.5 years of flawless observation, the Spitzer Space Telescope reached a pivotal moment its creators had long anticipated. The last drops of its precious liquid helium coolant finally evaporated into the void. This was the cryogenic heart of the observatory, the source of its profound cold, and without it, the telescope's longest wavelength instruments went blind. The super-cool detectors that had mapped cold dust and sniffed planetary atmospheres warmed up, their exquisite sensitivity lost forever. Many feared this was the mission's end, a quiet death in the deep freeze of space. But the engineers had a plan. This was not an ending. It was the beginning of Spitzer's second act, an unplanned chapter they called the Warm Mission. While 2 of its 3 infrared channels were now too warm to function, the shortest wavelength band remained operational. The telescope itself, now hovering at a frigid -240 degrees Celsius, was still far colder than any instrument on Earth. This remaining vision was perfectly tuned to see the glow of asteroids, the heat of distant stars, and the transit of alien worlds. The team had to reinvent the observatory's entire purpose. They developed new calibration techniques to account for the warmer temperature and devised observing strategies that leveraged this one good eye with brilliant efficiency. Spitzer, the retired cryogenic marvel, was reborn as the most sensitive exoplanet hunter in history. Its stability and its remaining infrared sight became the perfect tool for the long, patient stares required to find other worlds. This decade-long second life was a testament to human ingenuity, a triumph of adaptation over adversity. The mission that refused to die in its planning stages now refused to die in orbit, proving that a tool's usefulness is limited only by our creativity. What other aging machines, written off as obsolete, might still have a vital role to play if we learn to see them in a new light? Spitzer's Warm Mission continued for another decade, far outlasting all expectations. It kept its single infrared eye open, patiently watching alien worlds cross their stars and charting the dusty architecture of nearby galaxies. But even this remarkable second act had to reach its final curtain. The same orbital mechanics that gave Spitzer its perfect, cold environment now conspired to end its mission. As it trailed farther and farther behind Earth in its journey around the Sun, the spacecraft's distance made communication increasingly difficult. Its solar panels, angled away from the sun for all those years, could no longer generate enough power to operate its instruments and keep its antenna pointed at Earth simultaneously. The telescope was drifting into an inescapable silence. On January 30th, 2020, after 16.5 years of profound discovery, the project team sent the final command to put the observatory into a permanent safe mode. They shut down its transmitter, severing the last link with Earth. Spitzer did not go out in a blaze of glory. It simply went quiet, its eye closing as it continued its lonely, eternal orbit around the sun, a silent sentinel in the dark. Its physical mission was over, but its true legacy was just beginning to unfold. Over its long life, Spitzer had collected a staggering treasure trove of data. It beamed back more than 36 million raw images and observations, a vast infrared library of the cosmos. This archive did not gather dust. It became a living resource, a permanent gift to science. Every new observation, from the birth of a star to the atmosphere of a distant world, was meticulously catalogued and released to the public, fueling discoveries by thousands of astronomers around the globe. The telescope's influence seeped into nearly every corner of modern astrophysics. Its data is still being mined today, yielding new insights about galaxy formation, the chemistry of comets, and the properties of exoplanets that were not even discovered when the telescope was still active. Spitzer's greatest legacy is this selfless continuity. It was not a solitary explorer. It was a foundational pillar, a surveyor that mapped the hidden universe so that future missions could build upon its work. The James Webb Space Telescope, with its own powerful infrared gaze, now looks out at the cosmos, but it does not start from scratch. It looks at targets Spitzer first identified. It uses analytical techniques Spitzer pioneered. It studies planetary atmospheres using a methodology Spitzer proved was possible. The old telescope handed the new one a detailed map saying, "Here, this is where the mysteries are." How many more revelations are still hidden within that library of 36 million images, waiting for the right curious mind to find them? Spitzer's silent orbit marks not an end but a handoff. Its legacy lives on most vividly through the colossal eye of the James Webb Space Telescope. Where Spitzer was a brilliant pathfinder, Webb is the fulfillment of its promise, a direct evolution of the infrared revolution Spitzer began. Think of it as a master painter who first sketched the outlines. Webb now fills in those sketches with breathtaking color and detail. The connection is most profound in the hunt for other worlds. Spitzer taught us how to measure the temperature of a hot Jupiter and how to detect water vapor in an alien sky. It proved the techniques were possible, turning a wild idea into a standard method. Now, Webb uses its vastly larger mirror and more advanced instruments to perform the same trick on smaller, cooler, rocky planets orbiting within the habitable zones of their stars. The questions Spitzer raised, it now falls to Webb to answer. Spitzer found the 7 Earth-sized worlds of TRAPPIST-1 and confirmed they were rocky. But do they have atmospheres? What are those atmospheres made of? Could they possibly support life? These are the very investigations Webb is now conducting, using a playbook Spitzer wrote. The same is true for the deepest views of the cosmos. Spitzer, working with Hubble, identified those faint red smudges as massive infant galaxies from the dawn of time. It revealed that the early universe was a surprisingly mature and bustling place. But how did these galaxies assemble so quickly? What are the properties of their individual stars? Spitzer gave us the map, and Webb is now journeying to these distant islands in person, using its powerful spectrographs to dissect their light and read the history of their formation. Every time Webb analyzes the atmosphere of a distant world or peers into the heart of an early galaxy, it is standing on the shoulders of the smaller telescope that came before. Spitzer's greatest gift was not just the data it collected, but the roadmap it created. It identified the most compelling mysteries and proved we had the tools to solve them. The torch has been passed, and its light now guides our deepest gaze into the cosmic dark. The true end of a great observatory is not when its transmitter falls silent, but when its data stops speaking. For Spitzer, the conversation is far from over. Its vast archive, a digital library of 36 million observations, remains wide open, a free and public treasure trove for the global scientific community. This open-door policy is one of the mission's most revolutionary legacies. A graduate student in Chile, a postdoctoral researcher in India, or a citizen scientist in their living room has the same access to Spitzer's raw view of the cosmos as the mission's own principal investigators. This democratic approach to discovery has sparked a continuous cascade of new findings. Years after the telescope itself was powered down, the data is like a rich, unexhausted mine. Astronomers return to it with new questions, applying fresh analytical techniques or combining it with observations from newer telescopes like Hubble or James Webb. They might pull an old image of a familiar star cluster and, using advanced software to sift through the noise, identify a previously overlooked brown dwarf drifting at its edge. Another team might reanalyze the light curve of a known exoplanet, finding subtle irregularities that hint at the gravitational pull of an unseen sibling world, a whole new planet hiding in data that is a decade old. Every one of these late-breaking discoveries is a powerful argument for the enduring value of foundational science. Spitzer was not built to answer a single question, but to illuminate an entire spectral realm. Its archive is a permanent celestial record, a baseline of the infrared sky against which all future change can be measured. How many more alien planets, how many more clues to galactic evolution are still encrypted in those silent streams of numbers, waiting for the right key to unlock them? Behind every data point and every silent image beamed back from the void was a team of people whose lives became intertwined with a machine. For the scientists and engineers who nurtured Spitzer from blueprint to legacy, this was not just a job. It was a career-defining marathon, a project that saw young graduates become seasoned experts, all while guiding a precious observatory they would never touch. They called themselves the Spitzer team, and they operated with the quiet dedication of remote caregivers for a fragile child millions of miles away. Their daily routine was a meticulous dance of planning and vigilance. They would receive the telescope's scheduled observations, translate them into thousands of precise commands, and beam these instructions into the darkness, hoping they would find their mark. Then came the wait, sometimes days, for the data to travel back. A single miswritten line of code, a tiny error in calculation, could potentially jeopardize months of work or even the telescope itself. The pressure was immense, but so was the camaraderie. They shared inside jokes about temperamental instruments and celebrated the most minor of victories, like a stubborn valve finally opening, with the euphoria of a major holiday. One of the most poignant stories from the mission involves the telescope's safe mode. Like a computer restarting after a crash, entering safe mode was a protective measure, but it was also a heart-stopping event for the team on Earth. They would receive an alert in the middle of the night, a signal that their distant charge had encountered something unexpected and had shut down all but its most essential systems. Immediately, a global response would ignite. Engineers would be roused from sleep, joining frantic calls from their homes in California, Massachusetts, and Germany. They would spend hours, sometimes days, painstakingly diagnosing the problem from a billion miles away, trying to piece together the story from a handful of cryptic error codes. The relief when they successfully coaxed the telescope back to full operation was a palpable, physical thing, a collective exhale heard across continents. These were not faceless technicians. They were people who missed birthdays and anniversaries to babysit a machine in solar orbit, who felt a personal, protective pride in every new discovery. They gave the telescope its personality, affectionately nicknaming its instruments and mourning the evaporation of its liquid helium coolant as if saying goodbye to an old friend. When the final command was sent to power down the transmitter, many of the team members who had been there since the launch watched the signal fade with tears in their eyes. They were not just shutting down a piece of hardware, they were closing a chapter of their own lives, a decades-long partnership with a silent eye in the dark that had, through their care and expertise, forever changed how we see our universe. A telescope orbiting in the dark of space might seem disconnected from our daily lives, yet the advanced infrared vision pioneered by Spitzer is already weaving itself into the fabric of our future. The same principles that allowed it to sense the faint heat of a forming star 1,000 light-years away are now driving a quiet revolution in technology here on Earth. This is the hidden legacy of space exploration, where cosmic tools trickle down to become societal benefits. Consider the medical field. Spitzer's detectors were exquisitely tuned to measure minute variations in infrared warmth. On Earth, this translates to thermal imaging cameras that can see inflammation and poor blood circulation long before they become visible to the naked eye. A doctor can scan a patient and instantly identify a strained muscle, pinpoint the early signs of diabetic foot disease, or even detect elevated body temperatures in a crowd, all through the passive, non-invasive lens of infrared. This is not science fiction. It is the direct descendant of the technology that mapped the warm dust between the stars. The same sophisticated sensors are being miniaturized for personal health monitors, potentially able to track blood flow and stress levels simply by sensing the heat from your skin. This cosmic vision is also transforming our relationship with the built environment. Spitzer had to be perfectly insulated to preserve its cold, a lesson in energy efficiency we are now applying to our homes and cities. High-resolution infrared cameras can fly over a neighborhood and instantly identify buildings leaking heat through poor insulation or faulty windows. On a grand scale, this technology allows us to conduct energy audits of entire cities, pinpointing waste and guiding retrofits that save millions in fuel costs and drastically reduce our carbon footprint. The telescope's need to stay cold is teaching us how to keep our planet cool. Environmental monitoring is another profound beneficiary. Just as Spitzer could detect specific chemical molecules in distant planetary atmospheres by their infrared fingerprints, we can now use ground-based and airborne infrared spectrometers to monitor air quality. They can identify pollutants like methane leaks from pipelines or carbon dioxide plumes from industrial sites with incredible precision, providing data to protect public health and enforce environmental regulations. Even agriculture is being reshaped. Drones equipped with infrared cameras can fly over vast fields, seeing which crops are stressed by drought or disease long before the leaves turn yellow. This allows for precise, targeted watering and treatment, conserving water and reducing pesticide use. The technology that revealed the hidden universe is now helping us cultivate our own world more intelligently and sustainably. From diagnosing illness in its earliest stages to safeguarding our resources, the invisible light Spitzer mastered is becoming a visible force for good, a silent partner in building a healthier, more efficient future. How many other solutions to earthly challenges are currently orbiting in the dark, waiting for their purpose to be discovered? Those brilliant infrared portraits of cosmic clouds and alien worlds did more than fill science journals. They ignited the public imagination, spilling out of the observatory and into our cultural bloodstream. Museums around the world now feature Spitzer's work as centerpiece installations. You can stand before a wall-sized, glowing crimson vision of the Orion Nebula, a place once invisible, and feel as if you are peering through a portal into a stellar maternity ward. These are not just pretty pictures, they are data-driven artworks translating the universe's hidden light into a visual symphony that speaks directly to our sense of wonder. In classrooms, Spitzer's legacy is a dynamic teaching tool. Students don't just read about how planets form. They can access the same telescope data that professional astronomers use, charting the light curve of a real exoplanet from their school computer and watching the graph dip as a distant world transits its star. This hands-on connection to real discovery transforms abstract science into a tangible thrill, showing a new generation that the universe is not a closed book but an ongoing, participatory mystery. How many young minds captivated by that glowing map of the Milky Way decided then and there to become the explorers of tomorrow? The influence reaches even further into the studios of artists and the storyboards of filmmakers. The ethereal, often surreal color palettes of Spitzer's images have inspired digital artists and painters who reinterpret the cosmos's hidden structures into works that blend scientific accuracy with profound beauty. Filmmakers and game designers study these infrared vistas to create more authentic, awe-inspiring depictions of alien star systems and nebulae, grounding their science fiction in the startling truths of modern astronomy. When you see a breathtaking cosmic backdrop in a movie, there is a good chance its design was influenced by the real data Spitzer sent home. This cultural seepage is vital. It reminds us that the drive to explore is not a niche academic pursuit. It is a fundamental human impulse, one that feeds our art, our stories, and our collective sense of possibility. The telescope did not just catalogue celestial objects. It became a wellspring for creativity, proving that the greatest discoveries not only answer our questions but also inspire us to dream new ones. The Spitzer Space Telescope was more than a collection of metal and silicon orbiting the Sun. It was a physical manifestation of a fundamental human trait, our relentless need to look into the darkness and ask what is there. This machine, forged from decades of perseverance, gifted us a new sense. It allowed us to perceive the universe not just as a collection of brilliant points of light, but as a landscape rich with the warmth of creation and the dust of beginnings. Its legacy is not merely a catalogue of discoveries from newborn stars to distant Earths, but a permanent shift in our cosmic perspective. Spitzer taught us that the most profound stories are often hidden, waiting only for the right kind of light to reveal them. The data it gathered will fuel scientific inquiry for decades, and the questions it raised will guide the next great observatories. Its true monument is not in the silent spacecraft drifting in the void, but in the ignited curiosity of every person who sees its images and understands for a moment that we are all connected to a vast, dynamic, and breathtakingly beautiful cosmos. The telescope's mission may be over, but the journey of discovery it started has only just begun.